start now. And usually, of course, many people will watch it afterwards as well. Typically, they watch about 500 times or 600 times afterwards.
Ooh la la, you make me nervous. Actually, it's like there's like one part.
It is a good advertisement platform. I was surprised, you know. I'm very happy because it talks about the success of SPICE, but okay. All right. So I think, hang on a second, Martin.
Should I already share my screen or?
Not yet, not yet. I'm going to share it. So I would like to share the screen here. And then first of all, welcome everybody that showed up. As you know, this is the welcome back to the online SPICE-SPIN+X seminar series that is led here by the Spin Phenomenon Interdisciplinary Center. And here, let me actually start the presentation. It would be easier maybe. And led to me by me and Karen Eversosite, who is now in Duisburg, and the SPIN+X's Collaborative Research Center by Martina Schliemann and Burkhard Hillebrands and Matthias Chloe in Mainz. This is a webinar format, so please write your questions in the Q&A or raise your hands after the talk, and then we'll share with you give you the platform and promote you to speak with it and ask the question to the speaker. And it's my pleasure to introduce the speaker today. That's Katja Nowack, who is a professor at Cornell University. She is, of course, did her master's thesis in Aachen, then did her PhD in Delft University, and a postdoc period there after moving to Molle's lab at Stanford University. And she's been one of the young research leaders looking particularly at magnetic imaging and new techniques, and to use that to uncover many exciting things in correlated phenomena and spin magnetic correlated phenomena as well. So with that short introduction, I would like to ask you, Katja, to please go ahead and share your screen, and welcome Burkhard.
Sure.
Everybody, I think Martin maybe might get there. And we will mute ourselves and then just let you talk.
So now I want to do, the green box here is my green Zoom box. Looks a little as if it's cutting off my slide.
It seems cutting off the slides for some reason, yeah. Are you sharing the whole screen, or you are sharing the...
sharing the PowerPoint. Let me try to...
Share the screen?
Share the screen, yeah, okay. Let's try that.
Try that. That's better. That doesn't, okay. Yeah, that's much better.
Okay, excellent. Thank you. All right, yeah, so thanks so much for the introduction. And yeah, I'm really excited at this opportunity to share some of the work that we're doing using local magnetic measurements at this wonderful online seminar series. All right, so let me start from a very broad perspective. And so right now, it's really exciting times, I would say, in condensed matter physics. And that is because our kind of capability to create new and clean materials has never been as advanced as it is now. And so these advances in material synthesis are providing us with access to an ever-expanding number of quantum materials. And there's only very few examples that I kind of note here. And of course, these materials hold the promise to realize fundamentally new physical phenomena, some of which are shown here. However, there's a challenge, and the challenge is that we really need suitable experimental probes to kind of locally survey the quality of the relevant materials, and preferably also probes that can directly provide evidence of the phenomena that we seek. And so what I hope to do in this talk is actually convince you that local magnetic measurements and local magnetic probes can at least help addressing this challenge. And the motivation is very simple. At a very basic level, many of the phenomena that we're interested in have moving charges and magnetic moments at their heart. And a moving charge and a magnetic moment produces a stray magnetic field. And so, at least in principle, a local magnetic probe that can detect this stray magnetic field should provide can provide a unique window into the behavior of these moving charges and magnetic moments.
Oh,
I see, that was unintended. And therefore give us a unique window in the phenomena that we're interested in. And so here I'm really thinking about those magnetic probes that measure the stray magnetic field above a material or a device. Okay, so how might this look in practice? So you can think about just measuring, for instance, the magnetic properties and the magnetic response of a material. Think of, for example, visualizing the presence of superconducting vortices in a piece of superconductor, and then also locally measuring its diamagnetic response. You can also use a magnetic probe to visualize how current actually flows in a device, and you can use them to visualize magnetic textures. One strength of magnetic imaging is that really it's not a surface-sensitive technique in the sense that magnetic fields essentially penetrate any top layer that might be on a material or device. Think of, for instance, a top gate, or we, for instance, do work on ionic gated devices. And so what that means is that you can image mesoscopic devices that come straight from the nanofacility. And finally, also I want to point out that when you think of magnetic probes, don't only think about magnetic imaging, you can also use them as essentially a very highly sensitive kind of local magnetic property measurement system. And you might be locally probing magnetic excitations or magnetic noise, or apply them to just samples that have an extremely small sample volume that you can't actually measure with any bulk probe. All right, so what I will do in the following 40 minutes or so is just show you 3 examples how my lab uses a local magnetic probe to look or visualize the properties of different quantum materials. And so we will look a little bit at imaging spatial modulations of superconductivity in these kind of microstructures here. We will then look at how we can use a magnetic probe to understand how the current flows in the quantum anomalous Hall regime. And then we'll also, this part will probably be very, very short. I will show you how we can use our magnetic probe to measure the diamagnetism of a van der Waals superconductor. And just to warn you, these last 2 topics are really still very much in progress, in the sense that we are still kind of working through understanding all the data that we have. So what I said today will reflect kind of our current understanding of our data. All right, keep that in mind when I go through those examples. Let's start here. So the material that we're going to look at is cerium iridium 5, and that is a layered metal with tetragonal symmetry. It actually has or shows heavy fermion behavior at low temperatures with a mass enhancement of about 30. And it's known to be an unconventional superconductor, likely with dx squared minus y squared symmetry. There's a puzzle in this superconductor, which is, or a puzzling aspect, which is that if you measure samples of cerium iridium 5 using resistivity, you will find a superconducting transition temperature of about, in this case here, 1.2 Kelvin. But if you use a thermodynamic probe such as AC susceptibility or heat capacity, you will find that the superconducting transition temperature is actually lower at about 0.4 Kelvin. And this puzzle has actually motivated my collaborator, Philip Moll, and his graduate student, Maya Bachmann, to study cerium iridium 5 through measuring microstructures that they fabricated using a focused ion beam. And so that is really what Philip and Maya are wizards at, is using a focused ion beam to kind of micro machine or carve a device out of a single crystal. And that really gives you precise control over the shape and the geometry of a crystalline device. How does this work? I'm going through this because it's kind of important that you know how the devices are made, or how they look like. Okay, so what you do is you take a focused ion beam and you essentially kind of carve out trenches, which defines a little kind of lamella or slice in the material. And then in a final step, you cut that lamella loose at the bottom. You take it out with a micro manipulator and place it on a pre-pattern that you can prepare in advance. You put a droplet of glue, and this is right where the lamella of the material is. You can then, in the next step, evaporate gold over everything. That essentially makes electrical contact between the lamella and this gold pre-pattern that you had prepared. And then you go in with a focused ion beam again from the top, and you free or remove some of the gold in the active area of the device. So that's the square here. And then you can also cut out trenches, which essentially define individual contacts to the device that you're making. And so here you see an SEM image of a final device. The active area is kind of the purple square here, and it is contacted in the four corners, here, 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 and here. And so this is a fun-apart device that you can do resistivity measurements on. And what Maya and Philip found when they were doing measurements on these devices is that, well, you can do the measurement in two ways. You can source a current between these two contacts and measure voltage here and here, or you can source a current between these two contacts and measure the voltage here and here. And what they found, depending on how they did the electrical measurement, they found different superconducting transition temperatures. Maybe the difference is not that dramatic here, but I'll show you in a minute that there's more devices that show more dramatic differences. And then also generally the resistance trace shows very different behavior. And that's counterintuitive, because either your device is superconducting or it's not. So there should be only one transition temperature that you detect. The same was true for many devices that they looked at. So here's another Thunderpower device. Here's a cross-shaped device. And so that is a puzzle, and that's a perfect puzzle to actually address with a local probe. And so the local probe that we like to use is a superconducting quantum interference device, or short SQUID. A SQUID in essence is just a simple. It's a superconducting loop interrupted by two Josephson junctions. The SQUIDs that we use are actually really large. They're not just a loop, but they're actually really stretched out very wide and have a twist in themselves. So here you actually see an optical image of the complete SQUID. And here I'm zooming in on the sensitive area. So this is what we call the pickup loop, which is the loop where we detect the flux, the magnetic flux that kind of penetrates this loop. And then there's also an additional coil on chip here, which we call the field coil, and I'll talk about that one in a minute. And so we take, and so the inner diameter of this loop right here is on the order of 1.5 microns in this specific SQUID. And so that combined with the height at which we scan actually determines our spatial resolution. And so we take this kind of SQUID and align it under a very shallow angle towards the sample, and then scan it around to create images. The instrument in which we are doing this is a dry dilution refrigerator, and so you see kind of a cut drawing of our system right here. Here you see a zoom in of the actual microscope that we use. There is a range of like piezoelectric coarse positioners, and then here is actually our scanner. And then in the far end here, this little board actually carries the SQUID you can zoom in one more step, and then you really kind of see the squid that's brought close to the sample by approaching it with this piezoelectric bender that essentially moves up and down. All right. Let's talk about how a squid actually, or how our squids actually see superconductivity. So I told you that we have this pickup loop, and then we also have this field coil. If we run a current through this field coil and measure the resulting flux in the pickup loop, what we essentially do is measure the mutual inductance between the field coil and the squid pickup loop. And if we do that above a superconductor, if we are really far away from the sample, which is over here, so that's the voltage that we apply to the piezo to kind of move the squid in close to and away from the sample. If we do this measurement away from a superconductor, we literally just measure this geometrical mutual inductance between the pickup loop and the squid. But if we approach a superconductor, then the superconductor is going to start screening the field that is generated by the current in this field coil. And we see this as a change in the mutual inductance between the two coils. And the closer we get, of course, the more dramatic that change is. All right, so here we're far away, and here we're really close to the sample. And the ability of the superconductors to screen the magnetic field depends on the London penetration depth in 3D and the per length in 2D of the superconductor. And so, of course, if I was to change temperature, so now the dark trace was kind of the lowest temperature, and then the more pink to orange traces are taken as we increase temperature. And so as we increase temperature, the ability of the superconductor to screen the field is diminishing. And so we see a less and less dramatic effect on our mutual inductance. And so I can kind of take these traces as a function of height above a sample, or I can just park myself at a fixed height and actually take images in 2D. And so this is what we're going to do to these cerium, iridium, indium 5 microstructures. So here's the sample again. And here is an image of that magnetic susceptibility, or just before I described this as the mutual inductance, but what it really measures is the magnetic susceptibility of a sample as a function of X and Y. And then, of course, while we take this kind of image throughout which we kind of modulate the current in the field coil at a fixed frequency. Of course, in DC, we also get a signal, and we just simply see the Meissner effect from the sample and a few vortices being pinned in the sample. But we're really interested in this imaging mode, and we actually simply use it in this experiment to just locally identify where's the sample superconducting and where is it not. So everything where you see bright color, it tells us that the sample is superconducting. Everywhere where you see dark or black, the sample is not superconducting. So here we're outside the sample, of course, but you also kind of can see the trenches that were cut into the sample using the focus ion beam. All right, so now we're ready to watch a movie. So now we can actually look at the superconductivity in the sample as we cool through the superconducting transition. Okay, let's hope this movie actually plays. Yes, here we go. So we start at high temperature and then cool down. And you just saw that there's already some kind of like little puddles forming in the four corners of the device. So I should point out this frame here that you're looking at is kind of a zoom in on the device right here. Let's go a little bit further in temperature. And what you see is that, let's stop here. At this temperature right here, where in this transport configuration we measure zero resistance, we actually have extended superconducting regions connecting this contact and this contact and this contact and this contact. But there's no superconducting connection between this side of the sample yet and this side of the sample. And then if we keep going, at this temperature right here, all four contacts of the sample are actually connected by an extended superconducting region. And if we go even lower in temperature, that superconducting region kind of fills out and becomes bigger and bigger and bigger. And then also other parts of the device start to superconduct. Okay, so we found a very simple answer. And maybe in hindsight, this may have been obvious. So we found a simple answer to what is happening in this unusual transport behavior. And that is just the superconductivity turns on in this device in a very non-uniform fashion. All right, and we can even go and kind of use this information to really understand some more details about the transport curve. For instance, we can understand why the inferred resistance in this measurement spikes here. And that is simply because if I imagine now the device in these replaced by a mini resistor network, if I look at this temperature, pretty much all these resistors are still finite. Once I hit this temperature, I should replace these 4 resistors here with a resistance equal to 0. And what happens actually then in the device is that the current that I source between these 2 contacts gets dramatically redistributed across the whole device. So suddenly, actually, there's no cost for the current to flow kind of along these sides of the device anymore. And so more current is actually in the end going to arrive across this resistor close to my voltage probes here. And so that causes the spike in voltage or resistance or inferred resistance at this point in temperature. Okay, and then if I keep going, then of course this resistor here will also turn 0 and we measure 0 resistance everywhere. Okay, great. Let's look at a second device. At face value, this looks very similar. It's also a square, with the only difference that now the kind of electrical contacts are in the middle of the sides. And so let's also look at a movie of this one, how it goes through TC. And so here now it's playing. We start with like these little superconducting speckles that are located kind of in these little bridges right here. And if we go to lower and lower temperature, now slowly we see something happening. There's something coming up here. These regions get a bit more elongated. At some point, we get something happening within the square coming up now. If we go lower and lower and lower, eventually kind of the whole square fills out and becomes superconducting as well. Okay, great. So that was a sample with somewhat different geometry, but not dramatically different geometry. But what's still remarkable is that each image in this temperature series was really qualitatively different in comparison to the other device. And so really the question that you've been probably already asking in your mind is, what is really the source of the spatial modulation or non-uniformity that we observe in the images? And the answer is actually strain. It turns out, if you think about it, these microstructures actually have a strain field built into them. And this is because the cerium iridium indium-5 is glued with a thin layer onto sapphire. And sapphire contracts during cooling, or thermally contracts not that much, about this amount. Whereas cerium iridium indium-5, being a metal, actually contracts a more substantial amount, about 0.3%. And so there's differential thermal contraction between the substrate and the actual device. And it is known that cerium iridium indium-5, or the critical temperature of cerium iridium indium-5, is actually sensitive to strain. And this, for instance, can be measured on bulk single crystals using hydrostatic pressure measurements. So if you press the crystal along the A-axis, TC goes up. If you press the A-axis is an in-plane axis. If you press along the Z-axis or the C-axis of the crystal, then TC actually goes down. And we just compare numbers. So the order of magnitude of the thermal contraction is like about 0.2 to 0.3%. If we take the elastic modulus, we can kind of translate that to a pressure scale, and that comes out to be a few kilobars. If we look here, a few kilobars of pressure actually shifts the TC by a few hundred millikelvin, which is consistent with the kind of modulations in TC that we see throughout the device. We can do a more careful job, and we can actually go into use finite element simulations, and we've done this in COMSOL to try and simulate what the strain field will look like. And so here you see actually simulated strain maps, 3 strain components for these for the first device that we measured. And now we can take the information from the hydrostatic pressure measurements and actually figure out how much TC should shift as a function of per kind of unit strain applied along the A-axis and the C-axis. And so from the strain maps, we can compute or predict a local TC map essentially for the device. And this is what is shown here. And if we kind of compare that to our data, we can do that by pulling binary frames from this map. So if we look, for instance, at 550 millikelvin, we can say, well, all the regions that are shaded in black here will not be superconducting yet, but all the regions within the device shaded in white will already be superconducting. And we can do that for different temperatures. And we actually find remarkable agreement between these simulated maps and the images that we've taken. And we can do that for the second device as well and find similarly good agreement. And so this is exciting because we solved this puzzle of what is the source of this unusual transport behavior. But we found also a way now to actually spatially control superconductivity, at least in a strain sensitive superconductor, simply through geometry. And so we make use of the fact that we can, or this would make use of the fact that these microstructures allow you to actually really create very complicated strain fields. And this is exciting because strain is a very clean tuning parameter. You do not chemically change your material. You could apply this potentially to a wide range of materials, essentially anything that is compatible with the focused ion beam. And you could also think applying this to different types of electronic order. So think about, for instance, magnetic order. The focused ion beam, so all these devices, I actually didn't point that out, were actually oriented along specific crystal axes. So that was always the A-axis and the C-axis. But you can cut the kind of lamellas that we work with. You can cut at any angle, so you can really play also with a crystal orientation. And so you can this approach gives you really a lot of flexibility to design fairly simple to highly complex strain fields. In this was also a cautionary tale. Which is that really fairly small, the strain fields weren't so high, but even small strain fields can, for some materials, have very significant effects. And then, of course, the whole puzzle started by assuming that the resistivity in the device would be uniform. And so here's also a cautionary tale that non-uniform resistivity in a material can lead to really hard to interpret electrical transport signatures. All right, so that was everything I wanted to tell you about these microstructures. And so let's move on to look at our second example. And so here we're going to try and figure out or visualize how current actually flows in the quantum anomalous Hall regime. And so I'm giving a mini primer on the quantum anomalous Hall, maybe effect, maybe a little naive. And so the quantum anomalous Hall effect occurs in magnetically doped topological insulator, where the magnetic order kind of creates a non-trivial gap in the topological surface state of the topological insulator. And that was, and this effect was the first time experimentally observed in transport by Chang et al. In 2013. Okay, so let's look at what how this roughly works. If you think about, so the quantum anomalous Hall effect is strongly related to the quantum Hall state. on a very naive level, how you understand the quantum Hall state is that you have a two-dimensional electron system and you apply a strong magnetic field to it. And the field is so strong that all the electrons go around in closed cyclotron orbits, whose radius is much smaller than the sample dimensions. And so all these electrons within go on these closed orbits, and then of course along the edges of the sample, and that's not in the schematic. You get skipping orbits along the edge, and those give rise to highly quantized transport coefficients. So you can measure rho XX in your device, and as well as the Hall resistance. And the Hall resistance is highly quantized, and rho XX actually falls to 0. And that's kind of the key signature of the quantum Hall effect. Of course, there's a lot more to it, but in sake of time, I keep it that simple. The quantum anomalous Hall effect, on a very naive level, you can think of replacing the magnetic field B by an extremely strong Berry curvature. And the Berry curvature gives an anomalous velocity correction to the motion of the electrons. And so it's that very strong anomalous velocity correction that then kind of sends the electrons on these closed orbits instead of the magnetic field. And so a similar thing occurs. You get these closed orbits within within the bulk of the system, and then you get skipping orbits going all around your sample. And the signature of the quantum anomalous Hall state is then also measuring quantized transport coefficients. So here's rho XY, so the kind of Hall resistance, and here is the plot of the longitudinal resistance. In the quantum anomalous Hall regime, the rho XY becomes quantized, and its value depends on the orientation of the magnetization in your sample, which sets the kind of the chirality of these orbits, and it persists. The quantization persists even at 0 magnetic field, since the magnetization in your system sample persists. All right, we are looking at one material system that realizes the quantum anomalous Hall effect, and in our case, that's chromium-doped topological insulator heterostructures. And this is in collaboration with Nitin Samarth's group and Raju Shang's group at Penn State. And so that is the structure of our the heterostructure that we look at, and then this film is patterned into a fairly large Hall bar that is about 75 micrometers across, and maybe 100 micrometers long between the voltage probes. And then it also has a top gate that's kind of like in this light yellow shade. If we perform transport measurements below 100 millikelvin on the sample, we do observe a quantized Hall resistance that follows the magnetization of the device, and then we see a longitudinal resistance that drops very close to 0. This is at a specific gate voltage of the device. We can also tune that gate voltage, and what gets revealed then is that we actually do need to adjust the backgate voltage to shift the Fermi level into the quantum anomalous Hall gap. And so we reach these quantized transport coefficients at a gate voltage of about a backgate voltage of about 100 volts. So you see here that we have quantized transport coefficients at this plateau down here in RXX and up here in RXY. All right, so our device does exhibit the quantum anomalous Hall effect. And now we start imaging. So first, let's just image a kind of a narrow slice of the Hall bar at about 100 volts. First of all, of course, in DC imaging, what we'll see is mainly the magnetization of the device, which is kind of here. But what we actually wanted to do is look at how the current flows in the device. And how can we actually see current? So we can see current because a current flowing in a device produces a magnetic field, a stray magnetic field. And if we and that's given by the Biot-Savart law. So the 2D current density in the device and the magnetic field are linked by the Biot-Savart law. And then we detect the Z component of this magnetic field. And it's important, well, we won't get into the details of current reconstruction, but it's somewhat important to also consider that there's actually a point spread function. So we kind of measure the convolution of the Z component of the magnetic field convoluted with the point spread function of our squid. That gives us the magnetic flux, and that's directly what we detect. And it turns out that if we take an image of this magnetic flux, a full 2D image, we can reconstruct the 2D current density from that image. Okay, so let's try and look how that looks. So here, so first of all, I now need to apply a current to the device, and we apply that current at a small AC frequency so that we can disentangle the magnetic flux that is generated by the current alone and the magnetic flux to just the magnetic order in the sample. All right. So here's an image of that AC flux that we detect. I could walk you through just interpreting flux signals. I can already tell you that the flux signal looks a lot like a current that is flowing in the bulk of the sample. And I just remind you, we are at about 100 volts where we actually measure quantized transport coefficients. We can actually do this current reconstruction. We can reconstruct the current from this image, and this is the image then that we get, where here the color intensity, so the intensity of the red gives you the total magnitude of the current, and then the little arrows indicate the directions of the current. So we see that there's little whirlpools of current, there's current flowing predominantly through the bulk. And what is really surprising is that when we went into this, we were expecting to actually see the current to be strongly confined along the edges, because we were expecting that the transport current that we apply is carried predominantly by the edge modes of the quantum anomalous Hall insulator. And we find that this is not the case. We can take this one step further. So now instead of actually taking a full image, we only kind of scan a single line across the sample. And then we continuously vary the backgate voltage. So what you see is kind of like a cut through the y direction of the sample. And then on the horizontal axis now is actually not coordinate, but it's tuning the backgate voltage. And essentially we tune the backgate voltage through this quantized plateau. And what is plotted is actually not the flux data, but we've already done a reconstruction. And what is plotted is the component of the current density that flows along the device. So if I call this the y direction, then this would be the x direction. So what is plotted is the x direction, or the x component of that current density. And so we observe this kind of interesting V shape as a function of backgate voltage across the quantized plateau. We see current starting out kind of in the bulk of the sample, but as we tune the backgate voltage, kind of it's bifurcating or branching in this way. And we also can say that this exact shape that we observe is independent of where exactly we kind of take the slice through the sample. And also we've observed this on two different samples made from the same film, but it's not a feature of the exact location nor a feature of this exact device. But nowhere in this, throughout this plateau, we actually see the current concentrate along the edges of the device. And the way, so this is something that was one part that is still work in progress. How we're approaching to understand this V shape and what is going on is what we think is going on is that there's band bending present in the device. and that we tune the Fermi level through kind of a structure as is schematically shown here. And what I think happens is that the whole current that we actually kind of visualize is really flowing in the incompressible stripes that form within the sample. And there's a clear evolution as we tune the Fermi level of where and how wide the stripe is within the sample. Okay, what we can also do is take an image of how the current enters the device. And what is interesting to see is that we actually see hotspots at the contact. So now, let me see. Now you see the outline of the hall bar here. This is the wide kind of source contact that we use to send current into the device. If the magnetization points out of the plane and we take an image, then we can kind of see the current enter the device in this corner. And I should point out, this is taken at a backgate voltage at which we have fully quantized transport coefficients. If we flip the magnetization of the device, now the current actually enters in the different corner of the source contact. And I should point out the transport or the current is actually sourced from contact 1 here, and that is actually drained in this voltage probe. And so that's why you also see strong flux signals in this contact here. All right, and this is at least somewhat expected if you take a kind of a more bulk perspective of what is happening in your device. And what I mean by this is that in the quantum anomalous Hall state, you have a quantized sigma xy transverse conductivity, and you have a longitudinal conductivity sigma xx that is going towards 0. So you're in a material that has an extreme Hall angle or extreme ratio of sigma xy by sigma xx that is much, much larger than 1. And if you actually look at how the current is expected to flow in a device that has this, you actually expect that the equipotential lines you can simulate and are actually kind of shown in this color graph here. They actually flow from one hotspot in the contact to the hotspot at the other side of your sample. And this is a graph of the equipotential lines, but the current actually, because of the strong ratio, essentially follows the equipotential lines. So you would expect your current to do something very similar. And we have some evidence of that happening in the devices. And finally, this is actually, these hotspots is also something that a long time ago was actually were actually observed in the quantum Hall state using a really fun fountain effect in superfluid helium. So this is kind of a quantum Hall device that has a film of superfluid helium on top of it. And these hotspots where the current was entering the device were visible by really bubbles forming right at the hotspots where the current enters the device. All right, so that was imaging current. We have one other imaging mode on this device, and that is we can modulate the top gate with a small excitation. And what that does, if we modulate the top gate, we modulate slightly the Fermi level or chemical potential in the device. And the reason we might expect a signal is that the Strader formula tells us that we should. So the Strader formula tells us that dm d mu, so how much does the magnetization vary with a variation in chemical potential, is given by the transverse conductivity divided by E. And this is true in the quantized regime, but this is also true while you're within the band of any any conductor. And essentially what this reflects is that the orbital magnetic moments of the charge carriers contribute to the total magnetization of the device, and their contribution varies as we vary the chemical potential. And so here we have again the DC flux image, and now next to it is plotted the flux signal that's associated with the small wiggle that we apply to the top gate. And we do clearly get a magnetic signal. We can do this similar to before. We can kind of take a single slice through the device and then continuously tune the backgate voltage. Now we do this over the full backgate range here. And we see that there's a clear evolution in the signal size. We can kind of think about the signal in really two ways in a way. We can reconstruct from our flux signal. We can choose to either kind of reconstruct the magnetization of the device, or I should say a change in magnetization in response to the voltage that we apply, which is shown here. That's this reconstruction here. We can also reconstruct from this flux signal a corresponding current density, which is shown here. And I just want to, and so then we would be saying we are modulating the magnetization in the device. If I choose to show current density, I would say we are visualizing how persistent currents flowing in the device get modulated. And I just want to point out the two are really equivalent. Essentially, think about how in a square, if I have a homogeneously magnetized square, I could either quantify the magnetization by, the actual magnetization in the square, or I could quantify it by telling you what the equivalent current along the edge of that square is. The two are really equivalent. Because of the Schrader formula, I like to think in this case about the magnetization. So let's do that. Let's look a little bit at the strength that we actually detect in this, what we think is the contributions of the orbital magnetization. We can, and I should actually go really fast. We can look at the signal and interpret it in terms of the Schrader formula. Of course, we're not straight out modulating the chemical potential in the sample. We actually do change just the voltage on the top gate. We can relate this though to dm mu, but then we need to know the compressibility of our system and also something about the capacitance, capacitive coupling of the top gate to the electron system. And we've actually also done, and this we can actually measure, at least in a bulk fashion, by doing electric field penetration depth measurements on the samples, which we have done at the same time. And these actually give you direct access to kind of the ratio of the top gate capacitance and the quantum capacitance of your device. And so we can compare our data to sigma xy, which we measure, and then multiply that with the capacitance ratio that we actually measure. And this gives us this black line here. So this gives us an order of magnitude that we should expect for dm dV. And so this is this black line, and then the colored in lines are actually just horizontal traces at 3 locations of this data. And so at least we get quite good quantitative agreement between kind of the signal size as we are fully tuned into the valence band and what we actually measure. So that's nice. And then we can also say that the decrease in signal that we observe here really coincides with sigma xy starting to strongly deviate from the quantized value in the device. All right, so we think we have some good understanding of what what we're imaging here. And it's worthwhile to point out that also if you compare the AC gating data, so the data where we modulate the top gate of the device, and compare that to the images of the current density, this clear V shape shows up in both of them. And it appears that the current really seems to be avoiding or flow around the V shape that we see in the AC gating. And so if we, the way we kind of interpret now this wedge that comes in or that defines this V shape is really that it's the valence band actually coming into the device in a non-uniform fashion. And that's the part of the device that actually gets develops a finite sigma XX, and so that is the area that the current tries to avoid, and that's also the area where sigma XY locally goes down, and so we expect a much smaller signal in the AC gating. All right, I should really wrap up this part, just run through this last part. That's more an appetizer or a teaser than I don't have really time to tell you much about it. But we are also doing work on van der Waals superconductors. And the challenge really here is that, well, first I should say van der Waals superconductors are amazingly interesting. There's many of them. You have a lot of tuning parameters and whatnot. But there's one challenge, and that is that the samples are essentially tiny. And so a very basic measurement that you want to do on a new superconductor is measure its superfluid or diamagnetic response. But for this class of superconductors, you really can't do that using a bulk measurement property system, just because the samples are atomically thin and at most laterally like maybe tens of microns in size, but not bigger. And so predominantly these have been studied in electrical transport. But we would like to kind of explore them through measuring their magnetic response. And the starting material, or the material that we got started on, is actually ionic gated molybdenum disulfide, which superconducts. So molybdenum disulfide superconducts if you put enough charge carriers into it, and the number of charge carriers needed are on the order of 10 to the 14 per centimeter squared. And so you need an ionic gate to actually get there. But we've managed to create an ionic gate. Actually, we use an ionic gel that's spin coated on top of our devices, and that's about 300 nanometers in thickness. And we can look right through it. And so here you see an optical image of a device. That's an MOS2 device, and here you see its superconducting diamagnetism. The spatial resolution here is terrible because the ionic gate is actually so fragile that we take any image from really far away. But we're actually not really after imaging here. What we really want to do is just park our squid on top of this device and look at the magnetic response as a function of temperature and also magnetic field. And so we've done that. We think we see some signatures of the VKT transition in these superconductors. And then we also see interesting features when we turn on the magnetic field that we think are associated with interesting vortex dynamics. I will stop here. Just everything that I told you about was focused on scanning squid microscopy. We are also working on other magnetic probes, including Hall probes made from arthocarbene graphene. And with my colleague Greg Fuchs at Cornell, we've actually built a scanning envy center, a microscope that's currently working at room temperature. And we're using that to study different antiferromagnetic materials. All right, with that, let me thank everybody that has helped with the work that I talked about here today. Let me also thank various funding agencies. And I will finish here so that we have a little bit of time for questions.
Okay, excellent. That was a very nice overview with a lot of exciting things. So now we're open for questions. Would somebody like to start? Usually people raise their hands. I'll ask a question in the meantime while people are gearing up on the quantum anomalous Hall effect that you observe. So I still didn't quite understand. So you're saying that the actual edge states or whatever you see, this bulk transmission is coming from an effective edge that you induce by the gating, or I wasn't quite understanding why the transport that was not edgewise, but in the bulk, whether it was created by this compressibility stripes across the sample.
See, so I think so. There's maybe so when we went into imaging this, we actually had a fairly naive expectation, which is we thought that we would see chiral currents flowing along the edges of the device, essentially. Mm-hmm. That is what the most
right. The theory, but it's usually not the case. In the quantum Hall effect, it's not usually seen that way either. It's actually
exactly. So now, so it is true. So had I given the talk only on the quantum anomalous Hall work, I would have given much more justice on all the work that has happened in quantum Hall. And essentially, we actually are on a big kind of rediscovery. Yeah,
I mean, it was observing the quantum Hall, this stuff, but it was not really going through the edges, but through these channels. Yeah. Right. But they're still incompressible channels. This is okay.
Yeah. So essentially, I think on a very basic level, we are just discovering that everything along those lines that was found in the quantum Hall state is also true for the quantum Hall state, right. Which maybe in hindsight is not that surprising. But I think still,
I mean, they serve similar purposes, I think.
Yeah. What is still a little bit new in a sense is like, so in the quantum Hall state, most of the work has been done by measuring local electrostatic potential and also directly electronic compressibility. And we really directly look at the currents. So right. Even like in the context of quantum Hall, that's maybe not shocking, but a new aspect. So we can really see that where the currents go, and yeah. Okay,
good. So let me take the next question. So I think it may be Gisela there or Schütz. Yeah, Gisela. Yeah, I can hear you. Go ahead.
Yeah, I have the question. Thanks for this very nice overview. How much you can increase the spatial resolution with your technique?
I see. So there's several. That's actually pretty. I try. So with the squids that I'm currently using, we could make the pickup loop that you saw smaller. But actually, like in the case of the squids that we are using, that wouldn't help much because there's two factors that influence your spatial resolution. It's the size of your sensitive area, and then also the height at which you scan. And it turns out because we have like this field coil on chip and some other additional circuitry that I actually didn't talk about that allows us to fully linearize the flux response. Our squids actually have a lot of topography. If you were to look at them from the side, they actually have a lot of terraces and steps and whatnot. Yeah. And so if I keep all that extra circuitry, there's actually no way for me to bring the sensitive area closer to the sample than maybe to within like 300-400 nanometers. Okay. And so we actually do have some squids that have that size of pickup loops. So we have some that have 300 to 400 nanometer kind of diameter pickup loops. We end up not using them much because the signal also goes down of the area. So we kind of like, we are dialing on like these micron scale ones. However, and so with our squids, I guess I'm saying like you could maybe get to 0.5 micron, but not better. There is a different scanning squid technique out there that was pioneered by Eli Zeldorf, and he essentially has a squid that's really fabricated on the tip of a quartz tube. And so both the squids can get extremely small. I want to say like tens of nanometers. And because you have this kind of like tip geometry, you can also get really close to the sample. And so in that technique, I'm not quite sure what kind of like the best spatial resolution and actual real images are to this point, but in principle, you should be able to get to like tens of nanometers spatial resolution. So you can push scanning squid towards that, but then you really have to kind of work in a geometry where you also can get the squid close enough to your sample. And then of course, there's also the MD centers, which is a whole different
But those are also 50 nanometers. Then now they're getting to that point.
Yeah. And so the probe itself is a point, right? It's an atomic defect. And there really the spatial resolution is always like the limit always comes from like how far away is the MV center from the object that you're measuring. And so, and there the challenge is to get the MV center, have a MV center with good characteristics that keeps good characteristics, even though it's very close to kind of like the boundary of the diamond. So when the MV center gets too close to kind of the boundary of the diamond, the properties degrade. And so I think that's kind of the challenge there. But
operate the NV centers at 50 millikelvin?
I don't know. I think in principle you can. I imagine it to be really difficult.
You would have to have an open. I mean, I think you would have to have the light, the system open, with a camera, that you can shine light through it. But in principle, yes, I think.
My guess is, and this is completely not fully informed, right? It might be that Patrick Melitinsky at Basel University actually has one of those, or is building one of those. I don't know if anybody else is pushing to millikelvin temperatures with that technique. Of course, you also can ask. It's not only that if you can get things in principle cold enough at at those temperatures, you also start worrying about like the quite intense microwave signal that you need to run the NV center and the laser. Are they actually going to heat up the adapton system that you're trying to probe, right? If I think about the quantum anomalous Hall effect, I'm not
you just need to find a room temperature quantum anomalous Hall effect, and then you'll be fine.
Okay, thank you.
So let's go first before I ask Igor and others to answer questions. There's a couple of questions that are written that they don't have microphones, so I'll read them to you. So Nazat, he wanted to know how the contribution of the bulk states in the quantum anomalous Hall effect measurement depend on the value of the magnetization, if you measure that, because you said you mentioned that you measure the magnetization directly.
Okay, can you say the question again?
So it's how is the contribution of the bulk states in the quantum anomalous Hall effect measurement depend on the value of the magnetization?
I see. So we don't have, we can only measure very close to zero magnetic fields. By the way, one other quite that's the fact that I'm very jealous about the nanosquids I talked about earlier. You can actually measure in a magnetic field. We can only with our squids measure very close to zero magnetic field. We can apply 5 millitesla or whatnot, and then things go crazy. I think our Josephson junctions just go crazy. And so meaning we're really limited to measure at the value of the magnetization that is remaining in the sample as we return to zero field. So we really don't have that as a tuning knob. So I think that by that I can't answer the.
There's no answer. We had to measure it. And then from Sasha Kalashnikova, he wants to ask a very basic question: is there any alternative way to image spatial distribution of superconductivity?
It depends on what is meant by that. Of course, if in a way, the data that I showed was an extreme example of a non-uniform superconductor, meaning that there's parts in the sample that were superconducting and some parts that weren't superconducting yet. So we can visualize that. There's also plenty of examples where we or also, of course, many other groups that do scanning squid microscopy look at, say, thin film superconductors, and you do see that there's non-uniformities or heterogeneity in the superfluid response. Right. So you can visualize that or measure that. And there's a difference between you might find both variations in TC across the sample, or you might just find that the TC is pretty much, it looks homogeneous, but still the actual superfluid response or penetration depth varies as a function of space. And so you can measure that, always with the caveat, of course, that the spatial resolution is set by.
It's going to be pretty bad,
yeah, on the micron scale, right? Like we can't look below that scale. And even if you think about it, even a micron scale is some non-trivial, can be some non-trivial kind of like average over like much smaller length scales that are underlying. Yeah.
So let's go next to Patrick and then to Igor. So Patrick, go ahead and unmute yourself, please.
Yeah, right. Can you hear me?
Yeah.
Yes. Hi, Patrick.
Hi, Katja. Very nice talk. Nice to meet you.
So do you have a millikelvin Henry center scanning microscope?
Yeah, that's he was going to answer that. That's why.
Actually, yes, it can work, and we're working on that. But
Right.
I'm not here to talk about my work. I had a question on your talk. But
Yes.
yes, I'm sure we have something to report in not too long. So actually, I had two questions, if I may. One is a technical one about spatial resolution in your susceptibility measurements. Is the resolution there set by your bias coil or by your pickup coil?
It's complicated.
Yeah.
It's complicated. It's some. I wish I had a good way to even like quantify that. But you're right. It is a function of both. One experiment that we at some point want to or should do is just kind of image kind of arrays of, say, superconducting stripes, like pattern stripes, and vary both the thickness and the distance between those stripes, and try to put like hard numbers on you know, that would allow us to put like some hard numbers on what we think the spatial resolution really is. But even if we had that number, it doesn't really answer the question if we kind of image a completely unknown non-uniform superconductor. What's the spatial resolution? So I'm kind of dancing around the number, dancing around the answer. It's complicated also because it's very hard to do the simulations. So if you try to simulate how even a pattern sample kind of responds to the measurements that we do, it's really non-trivial to do that. And so we can't really answer the question easily even by simulations. I mean, we can look at, say, line cuts through this kind of device, and you can see the trench, right, in the device, but you can also see that it's not turning fully black. Like there's no superconductor right here in this trench, and yet the color is still some dark purple. So even if we're in the middle of the trench, we get some a mixture of signal from this side and this side of the device. And the trench is, how wide is that? That's a good question. It's probably 5 microns in width or whatnot.
Okay, good.
Yeah.
If I may, just a second question, which is it's less technical. You showed in the second part how you do current imaging, and I was wondering whether you ever tried to apply this current imaging method to your superconductor sample to verify that the currents are indeed flowing around along the regions of increased superfluid density.
I see. So we have actually, I haven't shown that here, but in this specific device, in the CM-Iridium 5 device, we actually also have applied currents and then look how those flow. And we do see once, for instance, the whole device is really superconducting, that the current will kind of like go around the edge of the device rather than flow in the interior, as we would expect if there's like Meissner effect and whatnot also happening. So we can kind of see that. Yeah.
All right. Nice. Thanks a lot.
Yeah. Thank you.
So Igor, could you please mute yourself and ask your question? Thank you.
Thank you. First of all, thanks for such a nice talk where you presented a lot of puzzles for theoreticians.
Okay, great to hear.
Yeah, but my question concerns a heavy fermion system where actually one expects that it will be very sensitive to small changes because F electrons there form very narrow bands and they are on the edge of localization. And of course, electronic system reacts to this, and all strains are connected with distribution of electrons, piling up near contacts and so on. So question is whether you can say something about other fermion systems, and also to what extent wide band systems sensitive to this kind of measurements.
So what other systems might be?
Well, any superconductor which does not have F electrons.
So I mean, one superconductor that
another fermion system, for example, uranium system, uranium based, or something like that. So any heavy fermion system, I expect that they will react similar to this.
I think I would agree. I don't know, like, I mean, the literature really on kind of hydrostatic pressure measurements is also, I think, a lot of these compounds have been explored there too. I'm not quite familiar, like, which of the 115 kind of family members are very, like, what their respective strain sensitivity is. I can say that we have done also a little bit of work on kind of strontium luthenate, which is another superconductor that is very strain sensitive, or where TC is shifting a lot as a function of quite small applied uniaxial strain values. And that's really because the kind of Fermi, well, you can even go through some kind of a van Hoff singularity as a function of strain while you're deforming the Fermi surface. We are quite interested in applying these measurements also to, for instance, uranium ditelluride. But I'm not quite sure, like, I don't think that much is known yet in that case about the strain sensitivity. We've also had our eyes on UPT3, but to be honest, same answer there. I'm not quite sure how strain sensitive that is. The microstructures are also interesting for us, not just for the strain fields that we get, but also they are a very friendly measurement geometry. They kind of provide a very well-defined surface and kind of device structure. Whereas if we actually measure cleaved surfaces of single crystal superconductors, typically the measurements are a little bit more messy or a little bit harder to interpret, just because there's a lot of kind of like surface roughness and changes in height and whatnot. But I have a feeling that I'm not really properly answering a question, but
okay.
So,
then what about quality of contacts? You know that in the time when quantum dots investigated, there was very important to have certain quality of contacts, and your contacts are really metallic, and so no problem with this, yeah.
I think that
because paling of charge near contacts extremely depends on the shape of barrier.
Yeah, I fully agree. And I think that maybe this is like one interesting suggestion of where we should take this in the future. Kind of like explore these, like do the imaging that we do, and look at the effect of like making the contacts in different ways. I think right now there is almost only one. Well, I'm actually not quite sure. Like we have not paid great attention to exactly what contacts were used on these samples. We essentially went with the recipe that our collaborators use for the transport measurements. And so there was like, we didn't pay much attention to it, but I agree that given that we didn't see what we naively were expecting, we should pay more attention and kind of like revisit what was found for the quantum Hall state and really apply it here too. But I think that's, so one thing I could imagine is actually fabricate samples from the same film and then have different devices with different contacts realized on the same chip and really see if it makes a difference for how the current gets injected into the sample. And that's something that we could directly kind of try to actually see.
Okay.
But
thank
right
you
now
much.
we've only looked at this sample with that one type of contact.
So let me, one more question, because, then I actually segue a little bit into also the topological superconductivity. So Ellie, go ahead. So.
Hi, Katja. Very
Hello.
nice talk.
Thank you.
I have a question regarding the quantum anomalous hole. You showed this V-shaped. And part of the sample showed current in the opposite direction. Do you understand that?
No, we don't fully understand that. I can say that when we flip the magnetization, so you're kind of like, there's this bifurcation, and one of the bifurcated branches also has like a little counterflowing branch, right?
Right.
It changes.
But also at lower biases, you had half of the sample blue and half
I see. So there is something I didn't talk about at all, which is when we tune outside of the kind of quantized plateau, and meaning that when we go, when kind of a sigma XX really comes up again, we actually see very strong signals. If we take those signals at face value, they interpret them as currents, they actually, it's on the overview slide. Like we're looking at it. Like I think you're thinking about like these kind of signals. And these images were actually taken outside of the quantized plateau. And we see a lot of higher harmonics and nonlinear signals in that regime. So once the sigma XX becomes non-zero or substantial, we see a lot of heating effects, we think. And we are really trying, like, I think there, other than saying that we see strong heating effects, we can't say much yet. I'm not quite sure why. If you think about, like, if you look at like simple models of heating for finite sigma XX, it might actually well be that the electron system heats up not just a subtle amount, but all the way to a few Kelvin. But then we are not quite sure why that causes the strong signals that we see. It might be maybe that the magnetization itself ever so slightly changes, but that's an aspect we're very puzzled about still. But we do, like, the only thing that we do know is that they're related to strong heating effects.
What sort of currents you drive in this experiment?
So we vary the current in the quantum, but we go to currents as low as 5 nanoamps, very painful. Wow. I think the images that I show are typically at about 20 nanoamps, but we kind of verify then in the quantized regime that if we go to lower and lower and lower current, and the limit there is really 5 nanoamps, that nothing, at least qualitatively, changes in the images. And 5 nanoamps is a non-atypical current also for the transport measurements. And we also see in transport, once we're below 25 nanoamps, the transport is linear, and the plateau well defined. With all images, we also co-record kind of like what the conductivities are in the sample. So we kind of know when we are applying too much current to destroy the quantization, let's say. And that happens, like if you apply 50, 60, or 70 nanoamps, that's too much. Yeah.
Okay, thank you. Very nice.
Yeah, so we hope we can also say something about the breakdown, maybe, or something. But we'll see. That's something we're really still working through. And any thoughts are welcome.
Sure.
Well, Eli has a nice interest himself, yeah. So that's true. You have a wonderful talk last fall. Yeah. Good. So thank you guys once again, and all the people asking questions. And Katja, really, I hope you enjoyed the wine. It was definitely worth it.
I did. I have to confess that I told my husband we should keep the bottles until I've actually given the talk.
Oh no, you can.
They didn't make it through summer.
I didn't make it. That's not bad. Hope you enjoyed it. Yeah, good.
Yeah, we did. Thanks so much.
Very good. Yeah. Anyway, so with that, I think I'm going to stop here the streaming on the online side.